Hello, this is Mr. White, and this video is on derivatives and tangent lines. And oh yeah, this is the good stuff. Here are the two exercises I'm going to do in this video, as well as the times at which they occur in the video. And I'd encourage you to check out the introduction to this topic in our book on the derivative and tangent lines. It's got a little interesting history on how this topic was born back in a couple hundred years ago. But let's also get into why is it that we don't really understand tangency as well as you might think you do. Invariably, students come into the class and they say, I know what it means for a line to be tangent to a curve. And I'll grant you that you probably would recognize it when you see it. But when it comes down to providing an airtight, mathematically accurate description, students always seem to fall short. I think my favorite all-time description of what it means for a curve to be tangent to a line or vice versa is this idea that it's like a person with a big round butt standing up against the wall, barely making contact. And again, we kind of know it when we see it. We understand the mental image there, but hardly a mathematically rigorous definition. So typically in little kid math, the definition of tangency starts with, okay, a tangent line touches a curve at one point. That's usually the starting point. But then somebody will say, okay, well that's not enough, because what if here's a curve and here's the line, and clearly that is not tangent. Again, we know it when we see it, and we know that's not tangent. So then the definition typically evolves into, okay, well it touches at one point, but it can't really cross the curve. So here I see it crossing over the curve, whereas if I draw it like this, it doesn't cross the curve. Okay, well let's add that bullet point. But then let's ask the question, okay, if it really only touches at one point, what if the curve were to later on do something like this? And then I might say, okay, well doesn't that cross the curve or touch the curve at 2 points? And doesn't the tangent line here actually cross the curve? And then we say, okay, well, you know what I mean. It crosses somewhere away from the point of tangency, but I'm talking about what it's doing right here, not far away. And we realize that our definition is getting kind of shaky here. And then I might say, okay, fine, I got you. But what about a curve and a tangent line that looks like this? What if here's the curve and I want to draw the tangent line right there? Well, wouldn't the tangent line look something like this, and isn't it crossing the curve? Is that a problem? Is it not a problem? So at that point, students are usually inclined to admit that we need a more rigorous definition of tangency. And here it is. So now that you understand the problem with our traditional understanding of tangency, I hope you won't complain or gripe when you see that this is the calculus definition of tangency. And at least as of the recording of this video, in the year that I'm recording this video, we've already introduced this topic, and this should look familiar to you. We've introduced this in PreCalculus, so hopefully this is not too scary. But I've tried to give you a glimpse already into how limits are going to help us solve this problem of how do we find tangent lines to curves. And let me at the same time, here's the definition of tangency, and you see that we are using the traditional letter M to represent the slope of the tangent line. We see our rise over run, our delta y over delta x, as well as the little more grown folk notation here, using f of x instead of y, and the limit, of course. And let's go ahead and skip ahead a little bit, and you notice that just a couple pages later, at least in the current edition of the book that I'm using as of this recording, you see that a couple pages later there's this definition of derivative, and it sure looks an awful lot like that definition of tangency. And let me tell you before you panic here, don't worry too much about getting every little nuanced difference between or distinction between this definition of tangency and this definition of derivative. If you want to think of them as largely interchangeable for right now, I'm going to say that's okay. And later on in a live discussion, we can nitpick over what are the differences. But for right now, I would actually just encourage you to focus on this one here, the definition of derivative. And again, we've probably already introduced this in PreCalculus, and you've probably already seen that f prime notation. At least I'm counting on you having seen that as I go through this video. And let's review a little bit about what the structure means, because I certainly don't want you just memorizing it without understanding why all of that is there. Let me bring up the GeoGebra file here, and we'll say here that if I wanted to find the tangent line at this red point here, at the red point, I start by saying, okay, well, I need 2 points to determine a line. And so I've got the red point, and then I've got the green point somewhere else on the curve. And that certainly is not the tangent line, right? We'd call that a secant line. It cuts through the curve at 2 points. So that's a secant line, and I see that its slope is currently 8 over 2, which reduces to 4, of course. And in order to make this a tangent line, I want those 2 points to be closer together. So I'm going to start the process of bringing that green point closer to the red point. And we notice that the red line then starts to approximate a tangent line a little better. I see the red line is adjusting. I see that right now, as I've adjusted, the rise over run is now 3 over 1, which reduces to just 3. And if I keep bringing the green point closer together, or closer to the red point, I see how my slope is adjusting, and you can kind of start to anticipate what that slope of the actual true tangent line is going to be. And just when it seems like I'm about to get there, it seems like, oh, it looks like it's going to be 2. Oh, this is beautiful. It's such a nice, pretty round number, and my delta y, my delta x are getting really close to 0, but as soon as I actually try to make them equal to 0, I get indeterminate form. I get my rise or my run. Now that those 2 points are one and the same, but that means that my rise over run is 0 over 0, and I really don't have a slope here, at least when I try to calculate it without using limits. So again, we see the problem. We understand this need for limits, that limits ask what's happening as I approach that 0 over 0 indeterminate form. So we could tell there that the slope's going to be 2, and we could prove that mathematically, but we're going to actually go back and now do the exercises I showed earlier here, and those are going to be a little bit even more challenging. Again, presumably we've done a few derivatives already in pre-calc. So let's jump into that first problem there. Let's get these two out of the way. And we are tasked with 3 things here. We're to find the equation of the tangent line to the graph of f at the indicated point, and then we will use a graphing utility, aka our calculators, to graph the function and its tangent line and just see visually, demonstrate visually that they look like what we expect them to look like. And then it turns out there's a derivative feature on your graphing calculator that I probably haven't told you about yet. And that may excite you, and it is good stuff, but obviously we got to know how to do this without a calculator first. So let's dive right in here. Let's go ahead and find the derivative. And again, I would take a little more time and detail in doing this if we haven't already seen it before. But I urge you to go over your notes, pause this and go over your notes if at any point you're not recalling how this came about. So remember, the derivative is denoted by f prime of x, and that's how we say it out loud. We don't say f apostrophe, we say f prime of x equals the limit as delta x approaches 0, as those 2 points get closer and closer together, of the rise over the run. But instead of doing y2 minus y1, we did f of x plus delta x minus f of x over, and instead of x2 minus x1, we do, x plus delta x minus x. And again, I write it that way when I'm introducing this to students and renewed it to really see the sort of parallel here between the y2 and the x2 versus the y1 and the x1. But typically what you're going to see in a book is that typically they're going to go ahead and not include these x's. They're going to go ahead and let those cancel out. So feel free to do that if you like. That is our definition of derivative that I showed on the previous slide. So let's go ahead and implement that. Let's go ahead and do that for this particular definition of f of x. So that's the limit. And again, we've presumably done some that are a little bit more on the easy side. This is starting to get a little more complicated, but there'll be nothing that's totally brand new that you've never ever seen before. So f of x plus delta x, that's like taking 1 over x plus 1. That's my original f of x, right? And remember, f of x plus delta x is like taking out the x and replacing it with x plus delta x. And then minus the original f of x. all over, and I'll go ahead and just call this delta x now. All right? On paper, I'd probably move on to another line, but since I'm doing this on video form, I'm going to conserve space a little bit here by just stretching this out a bit. And this is where, since we have a fraction minus another fraction in the numerator, this is where I'm going to go ahead and do the common denominator thing, right? So we'll do x plus 1 on this expression, and then over on this expression we'll do the x plus delta x plus 1. And this is where students often start getting a little bit scared and feeling like this is getting really messy, these fractions within fractions. But hopefully you have a little bit of faith now that the algebra will all clean itself up. The clouds will part, the sun will come shining through. You better be careful, though, on distributing your negatives, as I've presumably warned you about already. So let's focus on this numerator here. And again, that's all over a big fraction bar. So let me do this big, long fraction bar. And as far as the numerator goes, or the two fractions in the numerator, notice that we now have that common denominator. So let's go ahead and tackle that. And again, let's not FOIL it out. Let's cross our fingers and hope that that cleans itself up in some miraculous way. Let's not FOIL that out. But it is now a common denominator. It is the denominator for both of these fractions up top. So I will just go ahead and address both of those fractions over one big fraction bar there. So the x plus 1 here gives me x plus 1. And then when I subtract the x plus delta x plus 1, remember, I'm subtracting it. I need to distribute that negative. So that's going to be minus x minus delta x minus 1. Pause, let that sink in. That's a huge point if you don't catch it again. Make sure you pause it and study that and see why that is. And again, that's all over delta x. And this is where students want to be lazy, not fill in the blanks. Please don't. Please just be diligent and disciplined. Write the limb. All right, and let's scroll down a little bit here. And here's where things start to clean up. An x here minus x, they cancel each other out. A plus 1 minus 1, the clouds are parting here. All I'm left with up top is a negative delta x. And so we get a good feeling that we're probably on the right track. So I've got that negative delta x over that ugly common denominator there, right? So x plus delta x plus 1, parentheses x plus 1. And that is all over another delta x. So let's go ahead and multiply by that reciprocal. And be careful here. I see a lot of students kind of sloppy in that multiplying by the reciprocal. And they even will tell me out loud, I'm multiplying by the reciprocal. But then they'll put the delta x up top. Not sure why that happens so often, but we need to be attentive to that and make sure that I multiply by 1 over delta x. And we see that's what's going to allow us to say, aha, that goes away. I'm taking the limit of this. And now I'm in a position where I can direct substitute and get a nice clean answer. So when I go ahead and direct substitute only for delta x. Now remember, it's delta x approaching 0, not x. So don't make the mistake of putting zeros here. You're plugging in 0 for delta x. And that's what's going to give us, I think I squeeze it in here, negative 1 up top, right? Negative and a 1 right there. And, oh, there goes the bell, of course. That's all over an x plus 1 times another x plus 1. Let's not FOIL that out. Let's just call that x plus 1 squared. And that, ladies and gentlemen, is our derivative. Just to make that a little bit more of a complete sentence, let me rewrite the f prime of x equals. That is our derivative. Now again, what does that tell us about the original function f of x? It tells us the slope at any x value. So let's see where we're at with regards to the original problem and what we are being asked to do. I've got the original problem copied down here. So, and I'm just bringing the derivative down. So again, we're certainly not done. But the derivative was really the hardest part of this process. So we're over the top of the hill, so to speak. But we still need to find the equation of the tangent line. And I remind you, this is not the equation of the tangent line. This is just the function that will, there's the bell again, of course. This is just the function that will tell us the slope of the tangent line. So let's think of what we're dealing with here. We're dealing with a function that is clearly related to the basic function 1 over x, but it's been translated to the left by 1. So let's start depicting what this looks like. We've got a function that, again, looks like our basic 1 over x function, which is this beautiful thing, which is called a hyperbola, by the way, I haven't mentioned before. And it's been translated to the left by 1 unit. So there's to the left. And let's go ahead and draw the new vertical asymptote here at x equals -1. And what is it we're trying to find here? Well, we want the derivative at this point, 0, 1. So we want the, we don't want the derivative, we want the actual tangent line, right? So we want the actual equation of this line right here. And what does that have to do with this derivative? Well, again, the derivative is what will tell us the slope. So let's go ahead and figure that out. What is the slope of this tangent line at 0, 1? Well, the derivative, or f prime of 0, and I'm plugging in 0 because that's the x value I've been given. If I plug in 0, that's going to give me -1 over 0 plus 1 squared. Again, I'm just plugging 0 into this derivative equation. And that's going to give me -1 over 1, or just -1. So the derivative just told me that the slope of this line, this tangent line, is -1. So that's a good part. We're well on our way to finding the full equation. Remember the full equation, we tend to like point slope form in AP Calc, and that's the one that looks like this. Y minus y1 equals m times x minus x1. That's sort of using the little kitty notation. The grown folk notation would be to say y minus f of x1 equals f prime of x1 times x minus x1. Again, I'm just saying the same thing, but I'm using the more adult calculus notation. And the good news is we've already got most of this information. You just need to identify it. We already calculated up here that f prime, that our x1 is 0, right? And we just said that f prime of 0 equals -1. So I'll put that here, -1. Remember, a lot of students put the full derivative equation here. You don't want the full derivative equation. You need to plug in the x1 and get an actual constant there. So times x minus 0, and then y minus, and that's where we're going to put the actual y value here, which was given to us in this case, but if it wasn't given to us, we could have plugged our x value, 0, into the original equation, and that would give us the y1. All right, so I'll put a 1 here. And again, this is something I probably told you before. You may stop right here and call it done. In fact, I urge you to do that on test. The only reason to go a little bit further and put it in slope-intercept form is to be able to check it on your calculator. And we were asked to do that in this problem. So let's go ahead and do that. That would simplify to -1x, or just -x. And if I move the 1 over, I see it should have a y-intercept of +1. All right, so either of those is valid. And when we look at our picture over here to the left, that seems reasonable, doesn't it? We expected a negative slope because it's going downhill. So we're not surprised by that -x. That seems reasonable. The +1, the y-intercept of +1, seems reasonable when we look at our sketch. So we're keeping our brain engaged and saying, does this make sense? Well, let's go to the calculator now and give us be extra sure. So I've typed in the original equation, and there we go. Here are my window settings here, by the way, -2 to 1 along the x-axis, and -5 to 5 on the y. So here's the graph, and if I go to y equals, and I type in that tangent line, -x plus 1, I hope it's going to be tangent. And it is. That may not look like a slope of -1, but remember, things are kind of skewed because of the window settings. I mean, if I really felt strongly about it, I could tweak those window settings, and let's make them a little bit tighter. How about from -2 to 3? But again, at this point, that's just sort of cosmetic. I just want to visually see, does that look tangent? And it sure does look tangent at the point 0, 1. So good. All right, so where are we in this problem? We have done part A. We found the equation of the tangent line to the graph of f at the indicated point. We've also done part B. We've used the graphing utility to graph the function and its tangent line. And part C is something you'll probably like if you're not already aware of it, is that you can actually get the calculator to just tell you the, not only the derivative, but the tangent line without doing all the algebra. Now, of course, you know better than to think that that means we're really doing calculus. You know you need to know how to do this by hand, and we'll continue to develop more reasons as we go on in the course why the calculator method alone is not enough. But let me go ahead and show it to you despite those warnings. I'm going to delete the tangent line that I have and go back to just graphing the curve. And I'm going to show you a couple different things on the calculator. I'm going to go to Second Calc, that's right above the trace button, and notice option number 6 there, dy over dx. That is another notation for derivative. I probably haven't introduced that to you too much yet, but just take my word for it for right now. Let's go ahead and go to that. I'm going to just press the number 6 on my calculator keypad. And I'm going to now type in the x value that I want. So remember, the x value that I wanted was right here. So I'm going to type that in. I just hit the 0 key and hit enter. And notice that it tells me that the derivative, the dy over dx, is -1. Again, think of that as the same thing as f prime of 0 in this case. Now, if you're wondering why is it -1.00001, that's our calculator being goofy, and we've seen that before. We should know that we'll just say that that agrees with our derivative value of -1, which we got right here. Now, even better, oh, the fun is not over here. Even better, this is probably the only time in this class that you'll ever go to this menu, but I'm going to go to Second, and then right above the Program menu here, right above it, it says Draw, and notice that option number 5 there says Tangent. So I'm clicking the number 5 on my keypad, and again, I'm going to type in the x value that I want, 0. I just hit the 0 key and hit enter, and ta-da, the calculator will not only draw the tangent line, but it gives me the equation as well. So here is the calculator screen, and it gave me the equation right down here. Again, I hope you don't think that's any kind of substitute for doing it by hand. It's a nice way of checking, but we absolutely need to know how to do that by hand. All right, that was example number 1. That was part C. That was example number 1. Hope that made sense. Let's go on to the second example, or the second exercise. Let's get that out of the way and bring this up here. Find an equation of the line that is tangent to the graph of f and parallel to the given line. This one is not terribly hard, but it's just one where if you don't have a good mental image of what you're trying to do, you run out of luck. So I'm going to go ahead and admit it's kind of hard to figure out what that looks like graphically. We should have some pre-calculus skills that would help us figure out what that graph kind of looks like. But let me go ahead and cheat just for time's sake on this video and bring up an image here. And this is basically what it looks like. And the x scale and the y scale are 1 in each case there, meaning I am counting by 1, 2, 3, 4, 1, 2, 3, 4 along each axis. So just for time's sake, I'll go ahead and show you what that looks like. And again, we're looking for, we are given a line here, a linear equation, and we should know how to graph that. Let's say that the graph ends up looking like this, and we'll find out if that's at all close or not in a moment. But just to conceptualize what we're being asked to do, I am asked to find the tangent line that is parallel to that given line. So I can see I have a tangent line at this point that's going to be very steep and is certainly not parallel to the given one. I can see that a tangent line over here is going to be very shallow and is not parallel. I'm looking for the one that is probably right about there and is parallel to the given line. So we need to understand the concept first, and now let's get into the actual execution of this problem. All right, we get the sense that we're going to need to know the derivative that will tell us the slope of the tangent line at any point on that graph. So before we focus too much on the line that we're given, we're going to put that to the side and again do our derivative using our limit definition of derivative. So we're focusing here on f of x, and let's go ahead and do the derivative. F prime of x, And as you saw in the calculator, you can also think of that as dy over dx, and I'll elaborate on that more in class. So f prime of x, or dy over dx, whatever you want to call it, they mean the same thing here, equals the limit as delta x approaches 0. And again, it's f of x plus delta x. I'm going to go ahead and just jump into what that actually is. If f of x is 1 over root x minus 1, if I replace that x with an x plus delta x, there is my f of x plus delta x, minus 1 over square root of the original f of x. That's our original f of x, square root x minus 1. And that's all over delta x. Yes, this one's a little bit ugly, but once again, we see we have a fraction within a fraction, and we're going to need to do the common denominator thing. So I'm going to go ahead and jump onto the next line here. Equals limit as delta x approaches 0. And on the top, I've got 1 over root x plus delta x minus 1. Let's do the common denominator thing. Let's go ahead and do a root x minus 1 on the bottom and the top, minus 1 over the root x minus 1. And let's do the root x plus delta x minus 1. So when I told you in pre-calc that we're going to be dealing with some really nasty algebra, oh, I wasn't lying there. Okay, and of course, pause as needed through the video. Make sure, in fact, I'd invite you to pause and try to see if you can go forward on your own and get the same result I do. So what we have here is, again, I'm going to do the same thing I did in the last one. I'm going to say I now have a common denominator here. So let me just write that. And again, not try to distribute it at all. So that's my common denominator up top. And here, and then as far as the numerator within the numerator goes, I've got that minus that, right? Avoid any temptation to try to combine those at this point. This is about as messy as we're going to get, at least in this introductory topic of derivatives, but for sure, throughout the course of the year, we'll get into some algebra that is equally or even more messy than this at times. I just have to warn you. All right, so let's just move forward confidently here. Let me move this over a little bit. And actually, not just to say, well, no, let me not be lazy. I was going to save time and try to rewrite that, but let me just go ahead and rewrite it down here. But I'm kind of thinking ahead as to what I want to do next. I want to, again, do the, this delta x down here, I really want to multiply by the reciprocal, right? That's really what I want to do there. So let me go ahead and do that up there. Again, just to save screen space on this video. And let's think of what we're going to do about that expression up top. This should look kind of familiar to you, but take a deep breath and make sure you're paying close attention and you follow all this. So up top, I've got that. Let me go ahead and write that. Square root of x minus 1 minus square root of x plus delta x minus 1. And on the bottom, I'm going to just rearrange the order a bit. I'm going to write that and then this. And that's sort of a personal preference, but you don't have to do it in that order. And let's think of how we have handled expressions like this before. Do you remember how we do that? We do this, square root of x minus 1 plus square root of x plus delta x minus 1. And then we, boy, cross our fingers and really hope that this works out, because we don't want it to get much uglier than this, huh? All right, there we go. Let's hope that this is the worst of the storm here. So let's go ahead and FOIL out the top, but not FOIL the bottom, and see what happens. So as I FOIL the top, as I do the first terms, I'm going to get x minus 1. Now remember that this whole structure makes the outer and the inner terms cancel. So these two outer terms are going to give me something really ugly, but it gets canceled out by these two inner terms. So thankfully, I don't have to write that. And now I just have to subtract the last term, this times this, and distribute the negative. So if I subtract that, I'm going to get minus parentheses x plus delta x minus 1. Again, the square root sides cancel. And in fact, just to save a little bit of space here, let me go ahead and distribute that negative. I'm going to get rid of that, and get rid of that, get rid of that. Make this negative, make this positive. All over a bunch of ugliness. And let me go ahead and just write it. Square root of x plus delta x minus 1. Aren't you glad you signed up for AP Calc? This is good stuff. And then times all this mess over here. And this is where students often get insecure and aren't sure if they're doing the right thing and think, am I just wasting a whole bunch of time going down the wrong path? Well, this is what it takes sometimes. Let's see what we got. And of course, put the limb here actually. But just when you are about to lose hope, the clouds are starting to part. X minus x cancels itself out. Minus 1 plus 1 goes away. And look at that. I've got a delta x up top and a delta x being multiplied down below. And I may cross those out, leaving us with just a negative 1 up top. So don't worry, ladies and gentlemen, we're getting close to the end of this derivative. I've got a negative 1 over square root of x plus delta x minus 1, and a square root of x minus 1, and a square root of x minus 1 plus square root of x plus delta x minus 1, all inside of parentheses. And when I go ahead and do my direct substitution, when I plug in delta x equals 0, that will be here and here. Look at what I'm left with. I'm left with a negative 1, and then I've got a root x minus 1 times a root x minus 1. That's just x minus 1, right? And then what do I have here? A root x minus 1 plus a root x minus 1. That's going to be 2 root x minus 1. Be very careful. Notice that, let me back up here, because this is a huge point here. Notice that here we're multiplying these two radicals, and that gave us the radicals canceled, and you got an x minus 1. But notice here you're adding, whoops, the two radicals. So the radicals don't cancel. Instead, you're going to get 2 root x minus 1. Again, some nasty algebra here. Let's put that in parentheses. And let's scroll down a little bit and look at what we've got. We've got negative 1. I've already done the direct substitution, so I don't need to write the limb anymore. And I've basically got x minus 1 to the 1 power times 2 to the x minus 1 to the 1/2 power. I'm writing it that way rather than in radical form, because now I can see that I can combine those into negative 1 over 2 x minus 1. And remember what we do to these exponents. We add them in this context, right? 3/2 power. So, wow, I know this is a long example. I promise you that's about as ugly as algebra problem as you're going to get in this chapter, in this introductory limits definition of derivatives chapter. And we're not even done yet. That is the derivative of the original function. Let's bring that back down here. So, all that way up here, let's bring this, let's go back down here and remind ourselves what we need to do next. Thankfully, the hard part is over. Okay, this is where we're at. We've got the derivative. We've got the function that will tell us the slope of the tangent line at any point along that original f of x. And we've got a line that we need to be parallel to. So if I recreate that picture that I drew a little bit earlier, again, I'm going to just cheat and bring this calculator version of the picture out here. Hope you'll forgive me for that. Actually, let me put it over here, because I want to focus on the line now that I'm supposed to be parallel to. And first thing I'm going to do is go ahead and, even though I've been saying that we like point-slope form better in AP Calc, I'm going to say let's go ahead and put this in slope-intercept form. There are no absolutes. There's always an exception to every rule I state. And if we put this in slope-intercept form, the y equals mx plus b form, we would get y equals negative 1/2 x, let's see, minus 7/2, or minus 3.5 if you prefer. And let's think of what that would look like on this picture. If I were to extend this down a little bit, there's negative 1, negative 2, negative 3, negative 4. And again, there's a y-intercept at negative 3.5 right here, right? And the slope's going to be negative 1/2. So the slope's going to be downward, not too steep. And let's, again, remind ourselves, what are we looking for? We're looking for a line that is parallel to that one. So we're looking for a line that looks like this. And a point of tangency there. And if I were to just look at this picture alone, I might think that the x value I'm going to get is somewhere around x equals 2 there. But again, it's good to have an estimate there, but let's see where this takes us. We notice that we don't really care too much about the y-intercept of this red line. It doesn't matter whether the y-intercept was negative 3/2 or whether the line was here or here or here. We really just care about that slope. We need the red line to be parallel to the green line. So how do we do that algebraically? Well, we take this derivative and we set it equal to the slope of the red line. Let's set it equal to. We want this tangent slope here to be equal to the slope of the red line, which we just said is negative 1/2. So let's follow that through algebraically. Let's multiply, let's cross multiply. So I do negative 1 times this denominator. That'll give me negative 2 x minus 1 to the 3/2 is going to equal negative 1 times 2. So it's going to give me negative 2. I'll divide both sides by negative 2, and that will give me x minus 1 to the 3/2 equals 1. I'll raise both sides to the 2/3 power. This is all that algebra that we should be comfortable with, so it doesn't slow us down here in grown folk math. And that'll give me x minus 1 equals 1, which, wow, that's exactly the same thing as I estimated it would be earlier. And so that seems consistent with what we're expecting. That's a good sign. And let's remind ourselves, what exactly was I asked? To find the equation of the line that is tangent to the graph. So I do need the full equation for the line there, right? But I know the x value is 2. And hang on, I applaud you for hanging with me this long. We're almost done here. Let's go ahead and get the full equation for this here. And again, just trying to clear up enough space here. So let's go back to our form. Y minus y1 equals m times x minus x1. Now, I already know what the slope is, right? I already know that the slope is negative 1/2. That's what we set it equal to. So let's go ahead and put the negative 1/2 right there. We just determined that and this is a little bit tricky. I really need to think of what we solved for here. That's really my x1 value, I should say. That's the specific point where the slope is negative 1/2. So don't plug that in for x. Plug that in for x sub 1. And what do I put for the y sub 1? Well, let's look at the original equation for this graph, which was 1 over root x minus 1. Again, f of x equals 1 over root x minus 1. And if I were to plug in the x1 equals 2 there, if I were to plug in an x value of 2, that would give me just 1. So that's my y1 value there. And I don't need an equal sign there, I need a minus sign. So guess what? That is our equation. Again, for checking purposes, even though we weren't told to check it in this case, I think it's an awfully good idea because that's a lot of work to be done. There's a lot of opportunity for error. So let's see. If I were to simplify that or put it into slope-intercept form, I'd get negative 1/2 x. Let's see, this and this would give me a positive 1. And then if I add that one over there, that'd become positive 2. So I'll let you check and make sure I did that arithmetic correctly. So there's my solution in both point slope and slope intercept form. And here's the big moment of truth. I bring the calculator up here. I go to second, draw, And then tangent, I'm going to press the number 5 on the keypad for tangent. And do you remember what I type here? I type in the x value, which already says 2, but just to be extra sure, I'll type in 2. Hold my breath. And victory is ours. I know it looks a little bit fishy there, but take a look at what the calculator tells us. The usual calculator fishiness is going on here. Instead of just saying negative 1/2 x, it gives us this weird negative 0.5000 blah, blah, blah x. We're going to say that's the same thing. We had a negative 1/2 x. We had a plus 2. And there we see a plus 2.000. Again, we've gotten used to these quirks by the calculator now. So you know what? I think that deserves a star there, a bunch of stars. Good job if you hung with it, and good luck doing that on your own. Of course, contact me if you have any issues.